All right. So where did we stop last week? Remember, we talked about the validity of an econometric study and how to assess that. And we distinguished two broad fields which can be discussed if you want to talk about validity. The first one was the external validity, which means that what you found for the population under study can be generalized or transferred or translated to other settings, for instance, to other time periods, to other countries, to other institutional settings, and so on. That's usually what you're more interested in. So in general, you would like to find something which is valid in general. And then the external validity of your study is, of course, very important. However, that's nothing to do with methodology. That's more something where you really have to argue from the substantive issues. So in that case, you need economic reasoning. You need to know what you're actually talking about in a very deep sense, in the fundamental sense, not methodologically. Which is why we didn't really talk that much about external validity. Internal validity, on the other hand, means that the econometric methodology you apply to the population under study is actually done correctly. So the internal validity is something which concerns the methodological validity of your study. And this is something that we should think about and talk about, because we have to really make sure that our studies are internally valid. And we talked about a number of problems that might occur. For instance, what we have already encountered before, the omitted variable bias. That's an important problem, a very important problem where the estimation might go wrong. So if you want to find the causal effect of one variable on another variable, and there are omitted variables in your model, then the causal effect will be estimated in the wrong way, and it must not be interpreted causally. So that's one important problem. We also talked about errors in variables, for instance, where I have shown you last week that, if the measurement of the regressors is flawed in a way, so if you have measurement errors in the regressors, then your estimation will also be biased, and not only biased but also inconsistent. So in that case, what you will get from the estimation is the wrong causal effect. It's simply wrong. Okay, so there are problems, and third one that we talked about last week was misspecification. So you assume a functional form which is not the correct one. For instance, you assume a linear model, but in reality, the relationship between the regressors and the endogenous variable is nonlinear. And in that case, of course, what you would get is also meaningless. There are two more problems I'd like to talk about that are threats to the internal validity. The first one is the sample selection bias, and the second one is the endogeneity issue. So let's first think about sample selection problems. Up to now, we always assume that we have a simple random sample, and that's also sometimes called an IID sample. IID stands for identically and independently distributed, IID. And it means that we have an equal probability for each observation to enter the sample. So this is usually satisfied in cross-sectional data, but it need not be. Okay? So up to now, we just assume that what we call assumption number 2 for the OLS setting is actually satisfied. But it could happen that samples are, in a sense, biased. And this problem happens, or can happen, if the sample selection is not randomly, or is not totally randomly, but in some way connected to the endogenous variable y. I will give you an example in a minute to make that clearer. And in that case, this sample selection can cause correlation between those variables that we use as regressors and the error term, so the x and the u. And we've seen that the correlation between the x and the u is a severe problem. We've seen that when we talked about omitted variable bias, and the reasoning, I'll come back to that after the internal validity topic. The problem is really severe. Okay, so in that case, we have to do something about that. And here's the example. Suppose we want to find out a finance question. Suppose we want to find out whether actively managed funds outperform the DAX index. Excuse me. How could we do that? Well, one idea is to do an empirical study. That's a good idea. And in that case, someone draws a sample of managed funds and then collects data and looks at the returns over the last 10 years these funds actually earned. And then the estimation is quite simple. Suppose we don't care about any omitted variables and so on. Suppose we only estimate the average 10-year return of active funds minus the 10-year return of the DAX index or some non-actively managed funds, for instance. And then the question is there a sample selection bias? And the answer is yes, there is, because suppose that we translate this question into a regression framework with a dummy variable. So in that case, we could say that the endogenous variable is the return of the fund, and we have a linear relationship, but only one dummy variable here and an error term here. The dummy variable is 0 or 1. It's 0 if it's not an active fund, so the DAX itself, for instance, and it's 1 if it's an active fund. All right. So, but what happens here? Active funds can go wrong. So in that case, they don't earn more than the DAX, but they earn substantially less than the DAX index, for instance, or they really lose a lot of money. And in the worst case, they just vanish. Either they vanish because they misspeculated and all the money's gone, or they vanish because the management says that the management of that fund is not sufficiently good, and they just discontinue that fund and repay what's left. Okay? So in that case, the bad funds, the bad managed funds or the poorly managed funds, they don't survive. And only the ones that do well survive. So if you sample from a set of active funds today, you will only sample from a set of funds that actually survived. And why did they survive? Well, because they performed better than the poor ones. So the return of the survivals is higher than the return of the non-survivors. And therefore, the sample selection is related to the endogenous variable. And the active funds that actually did survive are likely to have a higher positive error term, disturbance term, U. So there will be a correlation between this variable here, the active fund variable, and the error term, because the error term will tend to be positive for those funds which are active, so where this variable is 1, and they tend to be negative for those funds where this variable is 0. So the larger the active fund variable, meaning if it's 1, and the larger on average the error term. So there's a correlation between the dummy variable active fund and the error term. Okay? So again, we have a correlation between the regressor and the error term. And that's a severe problem, and therefore we should have to do something about that. So what could we do in this case? How could we avoid, in this setting, this sample selection bias problem? And well, the trivial answer is better sampling. Sometimes that's really possible. So for instance, in this fund setting example, it is actually possible because we could use a population of funds that started 10 years ago. So we don't look at the set of funds that are around today, but we look at the set of funds that were around 10 years ago, including those funds that have been discontinued since because they performed poorly or because they just went bankrupt altogether. So in that case, we have a non-biased population, and we look at all the funds, not only those that were continued, and we don't drop the discontinued funds in that case. So that's the better sampling option. And in this case, that surely is doable. Yeah, so there's no fundamental problem collecting data from 10 years ago. Yeah, it's a bit more work, but of course that's worthwhile the effort because you get the correct answer in that case. The second example would be to run a randomized controlled experiment. Well, this is what we started with at the start of the semester. So that's always an option. But as we have seen, always an option is a rather theoretical argument because in practice, these randomized controlled experiments are not really doable in very many cases. So for instance, the active fund management is one such case. I don't think that a randomized controlled experiment is really doable here to answer the question whether active funds are better than non-active funds. And finally, you can try to cope with the problem and model what's really going on, but that's beyond what we are learning in this course. So that it is possible, and again, as I have said many times before, you're invited to visit the courses on econometrics in the bachelor, but also in the master studies, because there you will learn how to cope with some selection issues. And sometimes there's actually no other way than to jointly model the sample selection process and the estimation of the regression. Okay, but we can't do that here. All right, so that was problem number 4. So we had omitted variable bias, we had the wrong functional form, we had the errors in variables, and we have the sample selection bias. And the last one I'd like to talk about today is already bridging the gap to the next topic. It's called the endogeneity. So far, we have always assumed that the regressor variable x has a causal effect on the endogenous variable y. And we tried to quantify this effect and use the causal effect for policy. But who's actually guaranteeing us that this is the correct line of impact? So who's actually saying that there's a causal effect from x to y, but no causal effect from y to x? But that could also be the case. It's actually quite a good exercise for you when you read about an empirical study, either in the newspaper, need not be in economics, it could be anywhere. When you read about an empirical study, to reverse the line of argument in the causal effect. So let's look at the class size example. Wouldn't it be possible that there's now also a causal effect from y to x? So in the class size example, usually most people think that the line of causal effect starts with getting smaller classes, and this will improve the test scores. But it could also actually go the other way. So if you have a district, a school district where the class scores are really, really poor, then there might be political pressure to put more resources into that district. And having more resources, the district is able to hire more teachers. So the class size will shrink. So if the test scores are really poor, then the class sizes will get smaller. That's also a line of argument. Yeah? And of course, the causal direction is different. So in the one case, we look at the causal effect of class size on the test scores, but it could also be that there's a causal effect from the test scores to the class sizes. And of course, that has to be taken into account when you are interested in the causal effect in the first direction. And it's really good exercise to try to find a story, to think up a story. It need not really be a convincing story, to think up a story where the line of causal effect goes in the uncommon direction. For instance, you sometimes read that eating chocolate makes you happy. And the line of reasoning usually goes that there's some kind of ingredient in the chocolate which makes you happy. But of course, it could also be the case that more happy people eat more chocolate. In that case, being happy induces more chocolate consumption, and the line of causal effect is just reversed. And you could even think of, well, more bizarre examples. For instance, it's obviously, I think today it's obviously true that smoking reduces your life expectancy. But even here, one might think of a causal effect which goes the other way around. Because if people know that the life expectancy is short because they are very unhealthy or live in very unhealthy conditions, then they might be more, they might have a higher propensity to smoke because the nasty side effects of smoking won't affect them because they die before these health problems occur. Okay? So in that case, again, the line of argument, the probably correct line of argument is that smoking will let you die early, but it could also be the other way around, that if you know that you die early, you are more likely to smoke. Okay? So this is a bizarre example maybe, but it's quite a useful exercise for you to try to make up stories where the causal effect goes in a direction which most people don't really expect. And it's surprisingly often the case that it's really possible to find this reverse causality. Okay, so what are the consequences? Let's go back to the class size example. What are the consequences of OLS regression when you ignore the causal effect which goes from Y to X? Well, let's write that up, write that down. So the first line is the regression that we have always looked at. So we have Y as a function, as a linear function of X, and we have an error term here. But suppose there's also a causal effect in the other direction, running from Y to X. Why is that a problem? Well, let's have a look. Let's assume that the error term is, in one observation, surprisingly large. In that case, a high error term will induce Y to be very high. So large U means large Y. We go down here. A large value of Y means that X will also be larger than usual if gamma is positive, or smaller than usual if gamma is negative. Let's assume that gamma is positive. So a large value of Y means a large value of X. So the line of reasoning starts at the UI, it runs to Y, Y appears here, and it goes to X. So a large value of U indirectly causes a large value of X, which then means that there's a relationship between the regressor and the error term. And that's always a problem. Okay? So assumption number one would be violated in this case. And the expected value of the error term given X would no longer be zero, at least not for all the values of X. And in that case, the estimator for beta 1, the slope coefficient, that's the causal effect we're interested in, would be biased and inconsistent. And we would have to do something about that. So in the class size example, let's have a look. So large value of U would mean a high test score. A higher test score means less resources and larger classes. So gamma 1 would be positive, probably. We haven't tested that, but we a priori think that it will be positive. So a high value of U would be associated with a relatively large value of the class size. So there would be a positive relationship between the error term and the regressor. Okay? And in that case, if the beta 1 coefficient is negative, I think we can safely assume that it is, then our estimator would be too small. Okay? So the positive effect of smaller classes would be hidden in this case. We would think that it's actually less than it is in reality. how can we cope with this endogeneity problem? Well, as usual, we could try to set up a randomized controlled experiment. In this case, the regressor variable, the exogenous variable, is just held fixed, and then there's no feedback effect of y on x. So in that case, we can just compute the causal effect as we learned in the first week. But in general, this is not really doable. Okay? So this is not really an option, and therefore we have to cope with this kind of endogeneity. And there are two approaches. The first one is the estimation of a system of interdependent equations. So we not only, going back to the previous slide, we not only estimate the first regression line, but both regression lines at the same time. That would be one approach. And the second approach would be to use instrumental variables. And that's the more usual approach and the simpler approach. And this is the approach that we are going to talk about next. All right, so this will be the next topic. But before I start with that, let me briefly show you a little plot that illustrates why this relationship between this correlation between the error term and the regressor is really a problem. So let me stop the screen sharing here and start the screen sharing here. All right, suppose that we have a regression from from y on x, y against x. And we have a true regression line, which might look like this. And then we have our observations, which are scattered around this true regression line. But suppose now that the relationship y equal beta 0 plus beta 1, xi plus ui, suppose that assumption number 1 is violated. Which means that the expectation of u given x is not 0. Suppose for a minute that it's positive. So we have positive correlation between x and u. The same problem can be analyzed if the correlation is negative, but suppose now, just for the sake of the argument, that it's positive. What happens then? Well, a positive correlation between x and u means that the error terms tend to be positive, larger than usual, if x is larger than usual. So if we are in this area here, so if we look at the large values of x, then the error term tends to be positive. Not always, but on average. So let's put a few dots here. Not all of them are positive, but they tend to be positive. While if x is small, in this area here, the error terms tend to be negative. Not always, but on average. So let's put some dots in here. So this would be the cloud of points if we have a correlation between x and u. In this case, a positive correlation. And I think it's obvious that in this case, the regression line that you estimate would look something like this. So this is the estimated regression line. And this one is the true regression line. And obviously, even if you sample more data, then you get a denser cloud of points, but the problem won't go away. Okay? So you will still get an upward bias in the slope coefficient. So this line here is steeper than this line here. Okay? So it's a biased estimation and it's inconsistent, which means that even if you have a very large number of points, you still get the wrong value. Too steep in this case. And of course, if the correlation would be negative, then large x's would be associated with small values of u and small x's with the large values of u. In that case, the slope would go wrong in the other direction. But in any case, this correlation between the regressor and the error term is a really, really severe problem. How could that happen? How could it happen that you have a correlation between the regressor and the error term? Well, that could happen, for instance, because of omitted variable bias. We have seen that. So this picture here might illustrate a case of omitted variable bias. It might happen if the regressor variable is measured in the wrong way. So if there's measurement error in the axis, then this will also induce correlation between measured x and u. So this picture might also indicate a problem in the measurement of x. It might also be the case that we have endogeneity. We have just seen that. So it might happen that the value of x is large. That if the value of x is large, then u is large because of this endogeneity problem. So a large u causes a large y, and the large y causes a large x. So large u would be connected to a large x. That's exactly the situation here. So there are many different problems which actually cause the same problem. And the problem is nicely illustrated, I think, in this picture here. So keep this in mind, because this illustrates why all these problems are really, really severe. This illustrates why we should really care about omitted variable bias and why we should care about measuring the axis in the correct way and why we should care about reverse causality. Okay, so this is really an important, really, really important point. Right, are there any questions concerning that? That's not the case. All right, so we have just seen that the endogeneity issue can cause severe estimation problems because there's correlation between the error term and the regressor. So we have to find a way to cope with this problem. And fortunately, the method which is possible to solve this problem is not only applicable in case of endogeneity, but also applicable if you have omitted variable bias or problems in the estimation of the regressors. And the approach to solving this problem is called instrumental variables. And what is an instrumental variable? Well, as the name already suggests, a variable is called instrumental variable or just an instrument if it's used for estimation, but if it's not a regressor. Okay. So a regressor is usually not used as an instrument, or we will later see that sometimes it is, but we don't call a regressor an instrument in general. And these instrumental variables can be used for estimation, and they can solve the problem where you have correlation between the error terms and the regressors. So they can solve problems that are caused by omitted variables, that are caused by endogeneity, or that are caused by errors in variables. So in those cases, instrumental variables might help. And I will now show you how this is done. All right, so let's start with the simple linear regression model. So we don't care about the number of regressors in this case. let's go back to the basics. So we have a regression line where we have the endogenous variable on the left-hand side, then the two coefficients, the intercept and the slope coefficient, and we have a regressor xi on the right-hand side. And we assume, in contrast to what we did before, we assume that there's correlation between the regressor x and the error term. So we assume that assumption number 1 is violated. Assumption number 1 states that the conditional expectation of the error term for all values of x is 0. But we assume that the conditional expectation might differ for different values of x. So for instance, be positive for large values of x and negative for small values of x, or just the other way around. And in that case, assumption number 1 is violated, and we would get a wrong estimation, at least a wrong causal effect estimation for the regressor. Now, the main idea of instrumental variable regression is to decompose x, the regressor x, into two components. I will call that the good component and the evil component. The good component is the component which is not correlated with the error term u. So we assume that x can be split up into two parts, one part which is not correlated with u, and the evil component which is. So I haven't said anything here how to do that, this decomposition of x into its two components, but let's assume that it is possible to do so. Then, since the good component is not correlated with u, it can be regarded as a regressor that satisfies assumption number 1. And we then, in a second step, estimate the slope coefficient beta 1 using only the good component, only the uncorrelated component. That's the main idea, and relatively simple idea, I would say, of instrumental variable regression. All right, so a bit of terminology. Oh, there's a typo here. It should be endogenous, not endogenous, and exogenous, not exogenous. But anyway, I think you know what it means, endogenous and exogenous. And from now on, I will call variables that are correlated with the error term endogenous, and variables that are not exogenous. Okay? So I think it's good parlance to talk about the right-hand side variables, x1, x2, and so on, in the multiple regression framework as the regressors, not as the exogenous variables, because as we can see here, the word exogenous is reserved for those regressors that are uncorrelated with the error term. But it is possible that some of the regressors are correlated with the error term. And in that case, we still talk about a regressor, but not an exogenous regressor or an exogenous variable, but we would call that an endogenous regressor. Okay? So regressors can be endogenous, those are the problematic ones, or regressors can be exogenous. Those are the ones that we have dealt with so far. And we use an instrument, let's call it Z, to decompose the regressor variable x into its two components, the good one and the evil one. We need two conditions for Z to be a valid instrument. The first condition is called the relevance condition, and it states that there must be some kind of correlation between the instrument and the regressor. So that's the relevance. In a way, it means that we can use the instrument to forecast values of x. Yeah? So there must be a relationship between the instrument Z and the regressor x. And the second condition for an instrument to be valid is called the exogenouity condition. And it states that there's no correlation between the instrument and the error term. That's the exogenouity condition. So two conditions. There must be correlation with x, and there must be no correlation with u. And then the instrument Z is a valid instrument. Okay, and then we perform what's called the two-stage least squares regression. That's really a time-honored estimation method. It's been developed almost 100 years ago, I think in 1928. So it's really very old, but surprisingly powerful. So it's still used today to isolate the good component and then do consistent estimation of the slope coefficient, which has a causal interpretation. All right, how does this two-stage least squares estimation method work? Well, obviously we have two stages. The first stage is to isolate the uncorrelated component of X, the good component, and just ignore the evil component, the one which is correlated with U. And in the second stage, we only use the good component to estimate our regression equation. Okay, so let's look at the first stage first. So how can we isolate the uncorrelated component of X? The idea here is that we can use the instrument to forecast the value of X. So we make a regression, which has nothing to do with the original regression equation we are originally interested in, but which regresses the regressor X on the instrument Z. Okay, so here X is on the left-hand side and the instrument is on the right-hand side. We can just perform the usual LM command in R to estimate this regression equation. And then what we get is an estimated value of pi naught and pi 1. And of course, the residuals V. Obviously, the component pi naught plus pi 1z, that's the one here, is uncorrelated with U. Why is that? Because U is not correlated with Z. So a linear function of Z is also uncorrelated with U. So this part here is, in a way, the good component of X. And the rest, which is here subsumed in the error term, is the evil component. All right? If there are any questions, just ask. I can't see the chat at the moment, so in that case, just unmute yourself and ask. All right. So we have the good component here and the bad component, the evil component here. And we only want the good component. But of course, we do not know pi naught and pi 1. Therefore, we have to estimate them. But that's not a problem. We can simply estimate the good component by using the estimated intercept pi naught and the estimated slope coefficient pi 1. So in that case, we would get what we call the predicted values. In this case, the predicted values of X being predicted as functions of Z, rather than the predicted values of Y being predicted as functions of X. Okay, so the predicted values of X are, of course, well, what we have learned about predictions. So we use the estimated slope intercept and the estimated slope. And then we get the predicted values of X. And even though these are not perfectly uncorrelated with U in finite sample sizes, they are uncorrelated with the error term asymptotically. We haven't really defined properly what asymptotically means here, but let me just state that it's almost true that these components are uncorrelated with the error term. So this is the first stage. We isolated the good component of X, the component which is correlated with the instrument, but which is not correlated with the error term. And since this component is not correlated with the error term, the bias problem just goes away. Okay? So we substitute the true regressors, the original regressors in the regression equation, by their good component. Okay? So we substitute xi by xi hat. And then we estimate this new regression equation. And since the estimated x values are at least approximately or asymptotically uncorrelated with the error term, OLS assumption number 1 is now satisfied. Okay, so it's violated if we use the original x's, because the original x not only It's not only comprised of the good component, but also the evil component. But we isolated the good component. We re-estimated the regression equation with the good component only. And therefore, assumption number 1 is now satisfied. And we can estimate the slope coefficient beta 1 just using ordinary least squares estimation methods as before. Okay, so this is what we do here. Then we get an estimator for the slope coefficient, which we call beta 1 hat 2-stage least squares. So that's the slope coefficient that takes into account the problem of correlation between the error term and the regressor. That's really a very, very powerful approach to estimation. And the good news is that this estimator here is consistent for the slope coefficient. It's not unbiased, that's a little drawback, but at least it's consistent. So if our sample size is large, and we normally do have large sample sizes, if our sample size is large, then we will be close to the true value. Large could mean anything between 50 and 10 million. So it really depends on the case, but usually 1,000 or so is sufficiently large. All right, let's have another look at this regression equation. So let's start again with the original regression. We regress yi on xi. So not on the good component here, but on the original regresses xi. Now we look at the covariance between the yi's and the instruments. Okay, so we look at the correlation between yi and z. That's the covariance here. So we look at the covariance of yi and the instrument. Well, the first step is to substitute yi by the right-hand side of the regression line. So instead of yi, here we have beta 0 plus beta 1 xi plus ui. And of course, here we still have the instrument. Okay, so that's the new line here. Now we look at this expression, at this covariance, and we can use the rules of calculus for covariances. And as you might remember, covariance has a certain linearity property. So the covariance of this sum here can be split into 3 covariances, the sum of 3 covariances. First, the covariance of the first component, the first summand and the instrument, that's the one here. Then the covariance between the second summand and the instrument, that's the one here, and the last one. Now we look at each covariance separately. The first covariance is the covariance between a constant, namely the intercept, and a variable. And a constant is constant, it doesn't vary. So there's no covariance because the variance or the covariance of a constant is always 0. Otherwise, it wouldn't be constant. If it varied, then it wouldn't be a constant anymore. Okay, so this is 0 because beta 0 is a constant. Let's look at the second covariance. Well, there's a multiplicative constant here, which we can move in front of the covariance. Right, let's do that. So we have beta 1 times the covariance of xi and zi. The covariance of xi and zi is not 0. This is an assumption. We assumed the relevance condition. The relevance means that there's a correlation between x and z. So this covariance is not 0. And finally, the last one is the covariance between u and z. And again, we have an assumption about this covariance. We assumed the exogeneity assumption. Exogeneity means that the instrument is not correlated with the error term. So if z is a valid instrument, then this term is not 0, and this term is 0. So 0, first term is also 0, and here we pulled our beta 1 in front of the covariance. Right, so let's rewrite that. So the covariance between y and z is beta 1 times the covariance between x and z. Now we move the covariance to the left-hand side, and what remains on the right-hand side is beta 1. So the slope coefficient beta 1 is the fraction of the covariance between y and z divided by the covariance of z and x. And now you can see why it's really vitally important that that this term here is not 0. So the relevance assumption, it really makes sure that the denominator in this fraction here is not 0. So without the relevance assumption, this beta 1 would not be identified, would not be properly defined, actually. So we need both assumptions. We need the exogeneity assumption here to make sure that this is 0. And we need the relevance assumption down here, because if the instrument is not relevant, then this covariance is 0. And it must not be 0 as a denominator. Okay? So this is an expression for the true parameter value. Of course, we do not know the true covariance, and we do not know the true covariance between x and z. So we do not know the true value of beta 1, but that's, of course, our starting point. We want to estimate our coefficient beta 1. And how could we do that? Well, that's pretty obvious now, because the covariance, remember that from descriptive statistics, the covariance can be estimated by the empirical covariance. So that's just the standard formula for the descriptive covariance between two sets of variables, y and z. So this is just the covariance formula that you have learned in statistics 1. And the same for the denominator, but we substitute x for y here. Okay. So if we have a simple linear regression of y on one regressor variable x, and if we have one instrument which satisfies the relevance condition, that the covariance between x and z is non-zero, and the exogeneity condition, that the covariance between the instrument and the error term is 0. If we have that, then we can estimate the slope coefficient consistently by dividing the covariance of y and z by the covariance of x and z. Okay? That is the different way to look at the two-stage least squares estimator. If you look at it this way, it appears to be different from the one we looked at here, where we really performed these two stages. But one can show that it's really just the same estimator. So this is just a different way to write that down in this particular setting. When we go over to the multiple linear regression model in more than one instrument, then they are no longer equivalent. But here, where we look at a single regressor and a single instrument, these two are just different ways to write down the same estimator, but it's essentially really just the same, just in different notation. All right, so if we have a law of large numbers, then the covariance estimator converges to the covariance. That's just the meaning of the law of large numbers. An average, look here, this kind of average, an average converges to an expectation, and therefore this empirical covariance will converge asymptotically to the true covariance, and the same is true for the denominator. This empirical covariance will converge asymptotically to the true covariance, which is non-zero. So the estimator will converge to the true value, which means that it's consistent. If our sample size gets larger and larger and larger, in the end, we will be very close to the true value. Okay? And we have seen that both assumptions for instruments are really necessary. We have seen that we do need the relevance assumption. Otherwise, this covariance in the denominator would be 0, and beta 1 would not be defined. And we need the assumption that the instruments are exogenous, meaning that they are uncorrelated with the aperture. All right, there's one classic example. That's the example where this approach to estimation was introduced for the first time in, I think, 1928, so 93 years ago. And that was a simple question. They asked themselves, how can we estimate the price elasticity of the butter demand? Okay, so simple question and really relevant question, not only for people who deal with butter, but for anyone who's interested in price elasticities, of course. And the price elasticity is very relevant for pricing policy. So this is not only an economically interesting question, this is also interesting for business. Okay? So what is the demand elasticity of butter? Well, fortunately, we have seen that elasticities can be framed in the linear regression model in a very easy way by using logs on the left-hand side and the right-hand side. So if our endogenous variable Q, the butter demand, the quantity, is taken in logs, and if the right-hand variable is also taken in logs, the price of butter, then the coefficient beta1 would tell us how much would the butter demand decline in percent if we increase the price of butter by 1%. Okay? So beta1 is the price elasticity of butter demand in this case. So beta1 is the coefficient we want to know. How can we proceed? Well, maybe the first idea is to collect data from different time periods. So we look at different quantities of butter that had been bought on the market in a certain region and the price in those periods. Okay? So we collect data about prices and quantities of butter for many periods. And then the usual OLS estimator of the elasticity of the slope coefficient is inconsistent because of endogeneity. Why do we have endogeneity? Well, the butter demand or the butter quantity that is traded on the market, of course, depends on the price. The higher the price, the less people demand. And the lower the price, the more butter people will buy. But there's also a supply side on the market. And if the quantity of butter is increased, then the price will fall. And if the quantity of butter for some reason decreases, because of a trade embargo or something, the quantity decreases, the price will go up. So we cannot really say whether the price determines the quantity or whether the quantity determines the price. And the reason is that quantity and prices are determined jointly by demand and supply. You have seen this picture, the holy cross of economists, so demand and supply curve. And if we recognize that the price and the quantity that we can actually observe, it's still written in German here, so if the quantity here and the price here that we observe on the market, if we recognize that these values are not only influenced by shifts in the demand or supply curve, but by shifts in both curves at the same time, then it's really hard to say something about the price elasticity if we only look at these red dots. So suppose, for instance, that in the first period our demand curve is N1 and the supply curve is A1, then we have price which is here and a quantity which is here. And then if the demand increases and the supply decreases, then we have a new equilibrium here with higher prices and slightly higher quantity. And if then demand goes up even further and the supply also increases a lot, then we have a new equilibrium down here where the price is lower again and the quantity is much, much higher. Now suppose that we do not know these three demand and supply curves. And this is the reality. We do not know where the curves actually lie. What we observe is only the intersection of these lines. So we only observe the red dots. And looking at the red dots, we cannot say anything about the price elasticity for butter. Yeah, suppose these are the equilibria that we observe. So the different combinations of price and quantity. And these dots are really just the results, the equilibrium results of shifting demand and supply curves. So putting a regression line through here would not be a demand curve. It would not be a supply curve either. So it's just doesn't make any sense to put a line through this cloud of points. Okay? And the reason is that we would be interested in the demand curve, but we can't conclude anything about the demand curve from these points here, because they are caused by shifts in both curves at the same time. But what would happen if we were able to only look at shifts in the supply curve? So suppose we were able to keep fixed, in a way, the demand curve, hold it fixed, and only let the supply curve shift. So again, we have these three supply curves, A1, A2, and A3, but now the demand curve is really just fixed here. And the 3 points that we observe are these 3 dots. Of course, we wouldn't measure them without any error, so they would be kind of noisy, but you can see here that if we were able to fix the demand curve and let only the supply curve shift, we would observe points on, or if it's noisy, near the demand curve. And if we then put a linear regression through these red dots, we would get an estimate of the demand curve. And also that is an estimate of the demand elasticity of prices. Okay, so in this example, we have a problem. We need changes in price and quantity that are caused by shifts in the supply curve alone, not by shifts in the demand curve. And that's the really great idea of the first authors of this two-stage least squares or instrumental variable regression. They realized that they need a new variable, another variable, that shifts the demand curve, the supply curve, but not the demand curve. So as an instrument here, we need a variable that shifts the supply curve, but not the demand curve. Because if that's the case, then we observe points that are on the demand curve. All right, that's the idea here. So if you were interested in the supply curve, then you would need an instrument that shifts the demand curve, but not the supply curve. Okay. And the example the authors used back in 1928 was the amount of rain in what they call the milk regions. Why is that an instrument? And why is it really a valid instrument? Well, what did valid instrument mean? It means that the instrument is exogenous, uncorrelated with the error term, and it's relevant, can be used to forecast the exogenous, the regressor variable. So is it exogenous? Well, the butter demand does not depend on the amount of rain. I think this is a reasonable assumption. So the demand curve is not affected by this variable. How about the supply curve? Well, the supply curve is affected by the amount of rain, because if there's more rain, there's more grass. And if there's more grass and more hay, then the cows give more milk. And if there's more milk, then the supply of butter increases. Okay? This is not just a theoretical or observed reasoning. This is really the case. So the amount of rain is actually related to the amount of butter that is produced. Okay? So the amount of rain in those regions would be a valid instrument because it's unrelated to the demand side. People don't consume more butter just because it's raining more. This is an assumption, of course, but I think it's a reasonable assumption. And the supply curve is affected by the amount of rain. Because if there's only little rain, the cows give less milk, and then the price increases. All right, so if we look at the two-stage estimation of the demand curve, we need an instrument, Zi, that can be used to predict the good component of the butter price. Then we regress the butter price, or here the log butter price on the instrument, elicit the good component, let's call that log butter price head, and use that as a regressor in the second stage. So in the first stage, we regress the log price of butter on the instrument. We compute the predicted values. The predicted values are the good component because they are uncorrelated with the error term. We use the good component to regress this regression equation, but we substitute the regressor by its good component only. That's the approach for two-stage least squares. And that's a good point to stop for today. Are there any questions? Okay, that's not the case. So thanks for coming. By the way, in the survey, a relatively small number of students said that they would be interested in attending the course in person, but I will try to organize that hopefully for next week. So I will give you more information about that in the newsletter. So maybe some of you can actually show up next week in person. I would appreciate that because just standing here in front of a computer is not that much fun. All right, so hopefully see you next week. Thanks again.